We now consider a couple of try me problems for the end of section 4.4 on equivalent force systems. And the first one we're going to take a look at is problem 498, which involves this thick circular plate used in a machine called a gyratory compactor. We take a look at the figure and we see that we have three parallel forces all acting in the z direction. We want an equivalent force system at point O, and if possible, an equivalent force system consisting of a single force specifying the x and y coordinates of the point where the force's line of action intersects the xy plane. Take a few minutes to try this problem yourself, so pause this video and then resume playing when you're ready to see a solution. So the first thing we'll note here is that we have a parallel force system, which means when we find the equivalent force system at O, we're going to have a single resultant force and a resultant moment that's perpendicular to that force. So part B will be possible. The equivalent force system at O will be reducible to a single equivalent force. The resultant force is very straightforward. Again, they're all parallel and they're all acting in the negative z direction. So we have minus 500, minus 600, minus 700 newtons, and that's just minus 1800 K newtons. Now for finding the resultant moment about O, we could do this with either a vector approach or a scalar approach. If I write it out first with the vector approach, that's going to be ROA cross FA plus ROB cross FB plus ROC cross FC. If we want to evaluate these with the vector approach, we can do that. It may be just as easy to evaluate them with the scalar approach. For the first contribution, ROA cross FA, we have a position vector that goes in the I direction, and we're crossing that into a force in the minus K direction. I cross minus K is going to give us J. If we like, we can extend this position vector out this way, and note that if we're crossing R into F using our right-hand rule, we are going to get a contribution that points in the plus J direction. So that's going to give us 80 millimeters times 500 newtons in J, and that's just 40 Newton meters in J. For the second term, I have ROB cross FB. Again, I could extend that position vector for the purpose of doing this cross, and you may be able to see that what I'm going to end up with is a line of action for that moment, which also lies in the XY plane and makes a 30-degree angle off the x-axis this way. So my moment is going to end up back in this direction, and I can see that that's going to have negative I and negative J components. So I could write this as ROB cross FB as 80 millimeters times 600 newtons. That'll be the magnitude. And then the direction will be determined by the unit vector that's shown as the green line in the figure, and going from O backwards in both negative x and negative y space. And that unit vector will be minus cosine 30 degrees in I, so that's minus root 3 over 2 in I, minus sine 30 degrees in J, minus 1/2 J. Now the 80 millimeters times 600 newtons will give us 48 Newton meters. And so for the time being, I'm just going to write that as 48 Newton meters on this unit vector. Now finally we have the contribution from FC. Here's our position vector from O to C. If I slide this out again, this one is maybe a little harder to see because of the perspective view, but if I cross that R into that force, I'm going to end up with a line of action that makes another 30-degree angle off the x-axis in this direction, and the nature of the cross is such that that force component, that moment from that R cross F is going to point in this direction, so it will have a positive I and a negative J component. And once again, I can write ROC cross FC as 80 millimeters, in this case times 700 newtons, on that unit vector, which is going to be root 3 over 2I minus 1/2 J. And again, that's going to be 56 Newton meters, root 3 over 2I minus 1/2 J. So those are the three contributions from our moments. Now we can put all that together. From ROA cross FA, I've got 40 Newton meters in J. And then we have plus 48 minus root 3 over 2I minus 1/2 J plus 56 root 3 over 2I minus 1/2 J, all Newton meters. And if we collect the I terms together, what we have is a 56 minus a 48 times root 3 over 2, and that ends up giving us 4 root 3 I Newton meters. We have a 56 plus 48 times a minus 1/2, which is 52, actually minus 52, plus 40, that gives us a minus 12 J Newton meters. So that shows us that our resultant moment has a relatively large negative J component and a smaller positive I component, and I'll just sketch that qualitatively over here. So it's going to be along this line somewhere, and it's going to be in this direction. And so the question becomes, what is this angle? I'll call this angle phi. So I've defined that angle off the minus y-axis, so I can write this as the arctangent of the x component, the 4 over root 3, divided by the y component. And I'll just use 12. I can see that the angle is defined off the negative y-axis, so I won't bother using minus 12. I'm going to get this small acute angle off the minus y-axis. 4 over 12 is 3, and so this is the arctangent of root 3 over 3, or 1 over root 3, and in fact that angle does turn out to be exactly 30 degrees. So that's useful. So I have a resultant force here that is 1800 newtons in the z direction down, and I have a resultant moment that makes this 30-degree angle off the minus y-axis. And so for part B, I can ask, where do I have to slide that resultant force so that I can replace that equivalent force system by just the resultant force? And so I want to know, what direction do I have to slide it? Do I have to slide it into the foreground or into the background, and by how much? So one of the things we can do here is we can note that the direction we slide this has to be perpendicular to the plane defined by both the resultant force and the resultant moment. It's going to be in the xy plane, and the direction we're going to have to slide it, it'll be somewhere along this axis, will again be 30 degrees off, in this case the plus x-axis in this direction. so that it's perpendicular to both the resultant moment and the resultant force. And the question now is, do I slide it backwards in this direction, or do I slide it forwards in this direction? In which direction should I slide it? You may be able to see that if we slide it backwards, here for instance, then the R cross F operation is going to give us a cross product that gives us a vector that points in the correct direction for the resultant moment. If instead we slid it forward, if we slid it in this direction, then the R cross F would give us a moment that goes in the opposite direction. So we definitely need to slide this into the background. The figure's gotten very messy, so I'm going to erase all this. I'll just note that if I want to find the magnitude of the resultant moment, I can take the square root of the sum of the squares, and that number turns out to be equal to 13.86 Newton meters. So my distance d is the magnitude of that resultant moment over the force, magnitude of the force. So I have 13,860 Newton millimeters over 1,800 newtons, and that gives me a value of 7.698 millimeters. So my view of how much it shifted in the background here is greatly exaggerated. D should actually be about 1/10 of that 80 millimeter radius that's shown in the figure. Nevertheless, we have to shift it slightly backwards in order to produce a resultant force at that specific location off that 30-degree angle that replaces the initial 3 parallel forces. If I want the specific position vector that goes with that, I would write this as d minus cosine 30 in I minus sine 30 in j. And for d equals 7.698 millimeters, this gives me a position vector that's equal to minus 6.667 I minus 3.849 j millimeters. Finally, for our last problem, we have a wrench equivalent force system problem written purely in symbolic terms. We'd like to determine the wrench equivalent force system and specify the x and y coordinates of the point where the wrench's line of action intersects the xy plane. Take a few minutes now to try this problem yourself, so pause the video and resume playing when you're ready to see a solution. For this kind of problem, we said that the first thing we needed to do was to pick a reference point about which to establish an initial equivalent force system before we proceeded any further, and we had the flexibility to do that anywhere we like. I'm going to pick the origin just because that seems like a reasonable place to start. I could pick a different point if I liked. But I'll pick the origin, and the resultant force will be equal to F. There's a component in y and a component in z. The component in y is in the negative y direction, so I can just write this as F on minus j plus k. For the resultant moment about the origin O, I will note that the force that's applied along the y-axis is going to contribute nothing to the moment about O. Its line of action goes through O, so the contributions to moment about O will occur purely from this force here, and I'll use the vector approach in this case. We have an R cross F, and the R is A units in I plus B units in J crossing into F units in K, and the I cross K will give us a component in the minus J direction. The J cross K will give us a component in the plus I direction, and that result will give us FB in I minus FA in J. Now for the second step here, we said that we needed to find how much of that resultant moment was acting along the resultant force. In this case, since the components of the resultant force are the same in J and K, let's just make a note here that I could write the resultant force as a magnitude, which would be F root 2 on a unit vector, which would be minus 1 over root 2J plus 1 over root 2K. This becomes the unit vector in the direction of the resultant force, and I'm going to need that for the next step. So my parallel moment is equal to the dot product of my unit vector along the resultant force with the resultant moment on the unit vector pointing in the direction of the resultant force. And so I can see here that when I take the dot product between UF and the resultant moment, the only non-zero contribution I'm going to get is from these two J components. They're both negative, and so we're going to end up with a positive value for the dot product of UF and MR, and that's simply going to be equal to 1 over root 2 FA. And again, that's on this unit vector, so that's minus 1 over root 2J plus 1 over root 2K. So our perpendicular moment is then the difference between the resultant moment and the parallel moment. So that's FB in the I direction minus FA in the J direction. And then we're subtracting off the parallel part. We have a minus sign first in front of the J, so that minus a minus is going to give us a plus 1/2 FA in the J direction, and finally a minus 1/2 FA in the K direction. So our perpendicular moment ends up being FB in the I direction minus 1/2 FA in the J direction minus 1/2 FA in the K direction. And so finally we have our last step where we're trying to find this point P in the XY plane. We don't know its coordinates, that's what we're trying to find. We have units, so many X units here along the X axis and so many Y units along the Y axis. Those are our unknowns. And we need to find the location of that resultant F parallel moment pair so that the moment of the force F produces the perpendicular moment component that we just calculated. So we can write that as we want to find P, position P equals X units in I plus Y units in J, such that P cross the resultant force equals the perpendicular moment. So I can write this expression by pulling out the force magnitude F, and then I have in the I, J, and K directions, I have the X units in I and the Y units in J I'm trying to find. The force components are 0, minus 1 times F, and 1 times F. And that left-hand side, I can see in the I direction here inside the cross product, I'm just going to get Y minus 0. So I'm going to have Fy in the I direction. And in the minus J direction, I'm going to have X minus 0. So I'm going to have minus Fx in J. And then in the K direction, I'm also going to have a minus X minus 0. So I have minus Fx in K. That's the left-hand side. And then that has to match the right-hand side, which is M perp, which we found to be equal to FB in the I direction minus 1/2 FA in J and minus 1/2 FA in K. So now we can see from this that the J and K components are essentially the identical equation. We have two unknowns and three equations, but if we've done this consistently, we just need two of those three equations to solve for x and y, and the third one should be redundant. We can actually see that the J and K components are redundant. We only need one of them, and so this is quite straightforward then, because it just tells us that to match, we have to have y is equal to b and x is equal to a over 2. So if we like, we can come back and just summarize this. So we had y was equal to b and x was equal to a over 2. That puts point P right here in the middle. We know that the resultant force and the parallel moment component are going to make a 45-degree angle off the xy plane. So we have a resultant force and a resultant moment pair, and the m parallel part is equal to 1 over root 2 FA.